Hi, I would like to demonstrate this proof of concept of a light field renderer that I've been working on for a bit. It's very much an exploration application so that I could play with the concept and build some experience. In the first part of the video, I will quickly review the features that I have implemented in the renderer. Then in the second part of the video, I will discuss more the technical side, the challenges faced, and some of the implementation details. The first feature is translation and rotation of the camera, as it's the main point of interest of light fields and of image-based rendering in general, that we can generate views for angles and positions for which there is no corresponding source image. So I implemented an orbiter control for the mouse as well as UI controls for playing directly with the values. It supports the 6 degrees of freedom, but there is however a limited volume in which you can travel and a limited set of angles to look at before you hit the boundaries of the light field. The next set of features is image size and field of view. That is possible because the field of view of the final viewpoint is completely independent from the field of view of the original images. We just include more or less rays. Next is the possibility to change the focusing plane distance. One challenge of light field rendering is scenes with a lot of depth variation. There are various approaches to the problem, and I have used the one where we have a dynamically positioned plane of focus, which helps the algorithm select the correct rays. I implemented bilinear interpolation at the camera plane through the concept of synthetic aperture, combined with the bilinear interpolation from the image plane that makes it a quadrilinear interpolation in the space of rays. I also implemented a few exploratory and debug features. An overlay of the camera positions in space, 4 render modes, basically relics of implementation milestones, but they also help visualization and understanding. And the final aspect is the third-person view of the whole geometry. The current viewpoint camera is seen and the original cameras that took the source images. The first room drawn goes to the focusing plane. So let's see how it works. One thing to note about this particular experiment is that it is 100% image-based rendering. In fact, it is entirely written using OpenCV and there is not a single line of GL code. The idea is to have 2 planes that will sandwich a slice of reality and capture all the light rays between them. On one of the planes we have a bunch of cameras that are collecting the light rays coming from the other side. Given the camera's field of view, it's not really a cuboid though. The foreplane is much larger and each camera is collecting rays coming from all directions. Seen from above, we have our 2 planes sandwiching reality, some cameras and an object in the middle. The user is an arbitrary viewpoint somewhere. Each pixel from the new viewpoint is a ray of light that can be approximated using the original rays we have captured in the cameras. In principle, if we want to synthesize an entire new viewpoint, all we have to do is find the best ray for each pixel. The thing is, we're not going to have infinitely many cameras. When the ray hits the plane and back to the source camera, the ray we are going to sample is not perfect. The resulting pixel is going to be a blurry mix between 2 wrong colors. If the user could interactively slide this plane, he could find a good spot where the object of interest is in focus. The second improvement is to reverse the loop. Each synthetic ray crossing the plane in the neighborhood of the camera will be sourced from this camera. We project this quad on the final camera to find the zone of the image that will be filled by this camera. We then project that new quad on the focusing plane and get a new quad there. Then we find the quad on the original camera image that will project to the quad on the focusing plane. Now we can map directly from the quad in the original camera to the corresponding one in the final image. With this technique though, each pixel in the final image is only coming from a single camera. Instead, we can combine the response from each camera and fade their contribution as we move to the next. For any given camera, we modulate the quad of pixels by an aperture texture that encodes contribution weights. Back to the test application. I started capturing larger light fields and experimenting. I found that one important shortcoming of the approach is the field of view. The viewpoint rotation is limited by the global frustum created by the outer cameras. With this approach, it is best to have a rather large field of view at capture time and then go back to a normal field of view for the viewpoint. In VR, it will be necessary to combine rays from several light fields or use a different parameterization altogether. Here is an interesting aspect. Two different borders can be seen, one blurry and the other one sharp. The blurry one is when the viewpoint position reaches the edge of the camera field. As we move past the last camera, there is nothing to compensate the fading of the aperture. It could be improved by using a special aperture texture for the cameras that are out at the border. The sharp border is seen when the field of view and the global frustum intersect. And that's it for this review and discussion of light field rendering. I hope it helps demystify the topic a little bit. In the future, I would like to try different parameterization and, of course, an implementation in VR. Thanks for watching!